opportunity to look at the vampir with the trace we already generated for an MPI+OpenMP application. And the next thing we want to look into until the lunch break is trying another benchmark, another small exercise application we have prepared that is using actually MPI+OpenMP and CUDA, so we can utilize the NVIDIA Kepler cards that are available at the PC system. Hasn't been prepared for all of the programming environments. It will only work with the GNU programming environment. So if you have been using like Intel or Cray so far, you need to switch to the GNU environment and then load all the modules as before. Or if you just loaded them anyway, then it's fine. So point you're at. You're also going to need cupti, obviously, again. And I've been told that the cupti 1.3 module is now the default, so module load cupti should also do it. To find out that our cupti installation has actually been built with CUDA support in there, you can use what is called the cupti info utility. And Brian is going to demonstrate that once he typed in all the swap commands. And cupti info is a very small utility program, comes along with the cupti installation, and it has a parameter called config summary, which will tell you the complete there you are. Okay, so actually we have CUDA support, and we'll also look into libCUDA runtime, libCUDA, and libcupti, and it can tell us that all the three are supported, which is mainly interesting for developers, people who install that, to see that everything is correct. So the source code for this benchmark is located in the same directory as beforehand. So you can just copy the tar archive from users course 01 and 0 directory to your local working directory in Scratch and untar it. And there should be a makefile and 3 directories called batch, bin, and source. And bin is empty right now, there's nothing in there. In batch, there should be 3 batch files available. One for a run without any instrumentation, one with a run with profiling enabled, and one with a run with tracing enabled. And we can have a look at the makefile. Yeah, exactly, there are 3 files. So the makefile is set up in a way that we define what's our MPI compiler and the C compiler, and this time we have to set the NVIDIA compiler as well for CUDA. And we set a couple of flags for CUDA, OpenMP, MPI, and so forth. And then the benchmark will build all combinations of those. So it will build a version that runs only with MPI, one that runs only with OpenMP, one that runs with MPI and OpenMP, one that runs with MPI, OpenMP, and CUDA. And if you scroll down a little bit further, you will see that there are like make commands for all of those. You don't need to change anything really in here. And for each command down here, there's also the prep statement, or the prep variable already set, which sets to cupti. You want to make sure that at every linking and compiling step, it actually takes the right, or configures the instrumented binary the right way. We set MPI and CUDA explicitly, or only CUDA, or only MPI, depending on what you want. Okay, so basically you don't have to change anything in this makefile. It should work out of the box, and you just need to type make in the main directory, and it will compile all the different versions and place them into the bin directory. Scroll down a little bit. Yeah, you have to replace it with uppercase N1, lowercase n2 for the number of nodes, processes. It's using one process per node, and it's using, in this case, two OpenMP threads per task. So OMP num thread is set to 2. We create an experiment directory prefix with trace, and this time we also set the cupti CUDA enable environment variable to yes. And I'm going to get details of that in a second as well. So this batch script doesn't do profiling, it only creates a trace, and we set the size of the CUDA buffer to a reasonable amount of memory. So it can work without setting this one by using the default memory size, or if you get like an error message from cupti that it dropped some records because of inadequate buffer size, will tell you to increase this buffer to what it believes is the right amount. So 512 megabytes is way too much for this small example, but we are short of memory here, so could as well do it. You can just go with sbatch and run the tracing job, or end the profiling job if you want both of them. But I think you have to wait until either of those completed until submitting the next one. Otherwise, you might run into problems with the experiment directory, temporary one. It will only take like a couple of seconds, like 20 seconds or something. Yes. So if it compiled, you have everything there.
Yeah, it's compiled.
That should
Super
be.
fast.
And but it runs like it's actually running, but then it's like echoes or
Yeah.
And could you show me the batch file you used? Yeah, you don't need to do that. It's probably not compiled with debug support anyway. But it doesn't hurt.
Oh, well, maybe because I'm running with the ID and not like core. That shouldn't be a problem.
Oh, that's actually a good question. I didn't think about that. Do we need to specify the course partition or the course reservation? Oh, okay. So that's probably why it does that. It's called course? Oh, I see. So did it work for you? It creates something. So for people for which, if you made it that far, so if you have created a trace file, just like the last time, go to your VNC sessions if you have any, and just use vampir on that trace file. You have to go to scratch, veins. But, yeah. You have to use trace and traces.ots. Yeah, did everybody get to open it in vampir? Could you slide a little bit so we can see the full text of the locations? Thanks. Okay, so if you made it that far, you're going to see that this time we have a trace with only two processes. There are two OpenMP threads per process, so there's the master thread and another OpenMP thread. And now we're going to have a CUDA location per process, which is the events that are happening actually on the accelerator device. So maybe a little bit about the Jacobi code. It uses static load balancing, so you can define the amount of work that's to be solved on the CPU part and the amount of work that's to be solved on the CPU. And I think in the setup example, we use 15% of the work for the CPU and the remaining part on the GPU, as the GPU is much more powerful in terms of computation. Another thing that we already see here is naming, for example, of this CUDA location. So it's giving the device ID, which in our case is 0, since it's the first device on each node. It's giving the stream ID of the CUDA stream, which is 2. Of course, for that CUDA 5.5, 2 is the stream ID of the default stream, and it's like marked with a unique number as well as an ID. And as with the other program, there's an initialization phase and a computation phase. And now we might want to have a look a little bit further in there. So just zoom into any area of the computation phase. So we see some of the details a little clearer. So further, so it's pretty repetitive process here, and it's always doing the same style of work, the same kind of iteration. So we see here there is a certain serial part on top, which is in the Jacobi function. There's an OpenMP part, and it's not very well balanced here, so this one is always faster than the other one, which has to do the serial part, and so it's waiting quite some time here in the OpenMP barrier. But the new interesting thing is that we now see what's happening on the device. It's only using one CUDA stream in that example, but if you would use like more than the default stream, you would actually see all CUDA streams here and all the CUDA kernels. So if you click on any of the blue activities, you see that it's stated as a CUDA kernel. And this particular one is called the Jacobi kernel, and there are two kernel types in here. It's called a Jacobi kernel and cupti kernel. And as with any other activity, you get the function runtimes and on which location it ran and so forth. You also get, can you zoom a little bit further into like that area here? Yeah, that's great. You also see those kinds of black lines here, which look totally alike to the MPI messages we have seen beforehand in the MPI code. But those are RDMA messages. So these are the actual CUDA memory transfers we're doing from the host to the device. If you click on them, it says that it's an RMA, it's a remote memory access. And it's also given us the direction. And if you would scroll further down here, I think it also tells us the amount of memory that has been transferred. Exactly. So the data rate is pretty nice, even though obviously 15 kilobytes is not really enough to saturate, I don't know, the 250 gigabytes per second that we have available. If you would look at, for example, for the copy kernel, can you zoom at like the end of it, this part, for example, a little bit further? Okay, you see here is the actual memory copy, which works in that case as a synchronization for that kernel as well. So this memory copy is enqueued into the same stream as the kernel, but since it's a blocking memory copy, we don't show it as a separate. Since it's a blocking memory copy, we don't show it on the device side, but it blocks all previous operations on the default stream, and so it implicitly synchronizes the kernel here and then does the copy operation. That there is this cupti library provided by CUDA. It's a tools interface library, and it provides us with, on the one hand, callbacks for API calls. So it tells us when did a CUDA memcopy happen, and which were the parameters of this memcopy or any other driver or runtime call. And it also provides us with the activities of what's happening on the device. But cublas is just only like a third part, or like a wrapping library with that regard. make a client to that. And cupti doesn't know about cublas. However, cublas is doing API calls internally, and it's creating memory copies and kernels internally. And the cupti library will tell you about those. You will get a whole load of API calls, and you will most likely get one kernel, depending on the cublas implementation. But I mean, sure, you could, when you're doing the cublas call, you could put a macro inside your code, and it would show that from like around this kernel on the host side, you were doing at one point of the call tree, the call stack, you were doing cublas, and then inside this call stack, if you open, if you would open that second icon here. Can you open the second icon? Yeah, exactly. So we say this is not launch Jacobi kernel async, but it's actually my cublas call, and then inside we do some driver calls, but there's no direct correlation between this kernel and this cublas call. Another thing that's interesting here is that we are seeing, for example, the CUDA runtime API calls. And I don't know how many of you do program CUDA. I think it was a fair amount, 6, 7, like that. So for others with CUDA, there are actually two APIs to be used. There's the runtime API, which is more like a level interface, very convenient, and there's also the driver API. It gives you a little bit more control of what it's actually doing, but it's much more low level, so not like OpenPL in that regard. And the interesting thing is that the runtime API calls all map to some one or more driver API calls. So we could also tell the cupti library to give us the driver API calls, even if you're doing the runtime API calls ourselves. So if you would, can you open the batch file once more? And here we have seen that we set the copy CUDA enable environment variable to yes. So yes, in that case, is only like shortcut, which means runtime kernel memcopy, which is all stated in the documentation, of course. And so it means for CUDA, capture all runtime API calls, capture all kernels, and capture all memory copies. But we could also replace this yes, and Brian is going to do that. For example, with driver and kernel, just for testing purposes. So we're now not going to get any runtime API calls, we only get kernels, and we're not going to get any memory copies. Submit that job and wait for a chance, and look at the resulting trace file in Vampir. You're going to see that it now looks a little bit different. And maybe you could do the following. Can you go to Window, please? Window. Oh no, sorry, it's File. And we can use the comparison feature here. So if you click at New Comparison Session, you see the currently loaded trace. And if you click at the plus button down here, we can load an arbitrary amount of other traces we want to compare with that trace. So we might just want to use the last trace we generated, which should have the CUDA runtime API calls in there. So if you go one step up in the directory, yeah, like that, one step up, and it should be the one that has been copied, which now has the hashtag, and you can press OK. And a new comparison window will open up, which shows both of these traces in comparison. And there are also, the background is color-coded, so you know which display belongs to which master timeline, for example. So could you actually drag this function summary down here, so they are just as aligned as they're downwards? Yeah, exactly. Almost. No, yeah, down. Yeah, like that. Thanks. So if you look at this trace, I mean, they look pretty much the same since they are instance So one thing about this comparison view is that Vampir doesn't align those traces for you automatically. For a couple of reasons. First of all, it's not necessarily the same program you're comparing. So Vampir doesn't know if the trace A and trace B are from the same program, and they couldn't be aligned at all. And it's also a fairly complex process if you would try to do that automatically. But what we can do is, can you zoom out to the whole timeline once again? Let's reset the horizontal zoom. You can go to File, up here on the left, and in your case, it's New Comparison Session. Since I'm in the comparison session already, it's Comparison Session View. If it's not only left click, then it's either Control or Shift left click, and I would go with Control first. Yeah, exactly. So if you hold down Control and then left click and drag, you can manually align these two so that they start, for example, at the same point, even though they have different initialization phases. And if you zoom in a little bit further into the beginning area, you could actually manually align so that, for example, these two MPI calls are aligned, or any of that. And now assume that you have the same deterministic application, but with two different workloads. Then you would see, okay, I'm not too interested in the initialization part, but with the actual compute part, are my iterations are shorter here, are they longer here, and so forth. However, there are other options in the manual, and I need to explain one during the OpenACC session, which are required to configure how certain CUDA features are handled in Scopy. For example, there's something called flush at exit, another option for CUDA enable, which means that at the exit of the program, force cupti to deliver all accumulated activity records to the Scopy measurement environment. This is kind of a workaround for a problem with certain CUDA applications, especially with automatically generated CUDA applications as in the OpenACC phase, because they're missing a function call that is basically in theory required by cupti, CUDA device resets. Otherwise, it's not a valid cupti program, but CUDA doesn't enforce you to save this function call. So it's only necessary if you're doing tools. For example, the PGI compiler doesn't generate this function call. But since this flush at exits can get you into trouble with some programs, it's not enabled by default. After that, I would like you to try out this property of the Jacobi code, that you can actually change the amount of work to be executed on the GPU and the CPU, and see how your trace differs then. And you can compare these two, like how does my trace look like if I'm having 50% workload on the CPU? How does it look like if I have 80% workload on the CPU? And go down to where the application is actually launched, here. And so this is the problem size, which is 4096 square in that case, and we don't want to change that. We want to change the 0.15 to, which means 15% on the CPU, to let's say 0.30, which means 30% of the work on the CPU. And on top here, yeah, we can leave that, and just resubmit your job. What you can do is you can start Vampir without any trace file appended, and you can then go to new comparison session, I think immediately. No, it doesn't do. It's probably going to ignore the second one. Yeah. Oh, no, it opens them separately. But since it opens them separately, try to go to Window, and File, sorry. comparison session, and they're both in here already. Okay, that's not too bad. So once you have done that, you will see that even without aligning the two, it's totally clear that this one took way longer than this one. Which basically is, since that is the later one, our CPU is by far not as efficient in computing this problem as our GPU. So if you put more workload on the CPU, which is already at its peak, we're just like reducing our total efficiency or increasing our total runtime. So if you have more workload on the GPU, the kernels are going to be a little bit longer, but the CPU must do much less work here. Yeah, it's right. Yeah, not noise, but it just takes different amount of time. Just as your MPI init call takes different amounts of time. Another thing is that if you're like working on a dedicated system, so you're getting the same graphics call over and over again, it's going to take way longer the first time you call it after a boot than over the next times you're going to call the same call. Because the driver has to warm up and get some settings done, and the next time it's already warmed up. Yeah, so we see here that each iteration is much longer than each iteration here. That should be fine, but you think you also have to adjust the CPUs per task here in the allocation. There's one process per node, so how many CPUs are there? I think there are 8 per node, right? Yeah. No, it's set to the OMP num thread directly. But I think this didn't happen on our on Tartarus interest. So it might be specific to this system. Yeah. Yeah. Yeah.